excited for today. Welcome, everyone. Excited to have Decarb Debrief episode 3 going today. And we have Kristin McMurry as our wonderful guest, and we are talking about Approaches Decarbonization Part 2. If you didn't happen to see Part 1, worry not. I think you'll still come away with plenty during this episode. However, I do want to just bring to your attention that all of the past episodes, slide decks, and video are on pipeline for you to check out. And I've heard really good things about from feedback from participants that they're really enjoying this content, that it is accessible to people and really well thought out. So that is a kudos to Kristin for all of the hard work she's put into this, and to the rest of the sustainability team who've worked really hard, and I'm glad that people are enjoying it. I just want to start by saying hi to Kristin again. For anybody that has missed the past session, Kristin, would you be willing to give a little overview of your role here at RMF and the team that you work with?
Yeah, so I've been with RMF for 9 years in the master planning department. So we like to look at a campus from a very zoomed out level. We look at the campus as a whole. So when we're talking about decarbonization technologies, it's usually something that we're talking about in a central plant setting or something that affects the entire campus. And we don't really dig into, every single building and air handling unit. We look at how can we, what changes can we make today that are going to impact the campus for the next 50 years?
Yeah, love that. And how big is your team again?
There are 5 of us.
Awesome. I forgot to introduce myself. So any of you that might not have been to one of these Decarb Debriefs yet, I am Wendy Placco. I am the Sustainability Program Manager here at RMF. And my role is to work alongside, we have a team of 3 that are on the dedicated sustainability team. And I work alongside them to not only deliver client work, but also to work on things like internal education here. I'm super excited to be offering this work. And one of our biggest goals with this series is to help make sure that we are bringing along the entire team with sustainability work, because it is so complex. We have we on the sustainability team work alongside master planning all the time, but we do have a lot to learn from the greater team as well. So while we are offering this education series, we definitely want to just start to get you involved so that we can learn from you as well. So with that, I think let's dive in a little bit. I'll give a brief recap of what we talked about last time and sort of tee things up for us to continue the conversation. Last time we talked about a few things, but mainly we talked about approaches to decarbonization, of how the master planning team starts a project. So they look at energy load profiles, they know about different low carbon technologies, and perform a quantitative analysis of cost, energy, and carbon. And with that information and some of the barriers and challenges that certain clients might run into with the system that we are suggesting for them, we then started to do a deeper dive into technologies that can produce steam. So we looked closer at industrial heat pumps. We looked at well, Kristin, can you help me out here?
We looked at electric boilers. We looked at SMRs.
Combined heat and cool, or
combined heat and power.
Yep. So we looked at those specific technologies in order to tee things up for today's conversation, which is hot water specific technologies. So with that, I think I'm going to share my slide deck and we will dive into today's presentation. And so as a quick recap, as we dive in, we wanted to reiterate this idea of coefficient of performance. Kristin, can you remind the group about that?
Yeah, so the coefficient of performance is sort of like talking about efficiency, but because we're often talking about moving energy rather than burning fuel or using electrical energy, sometimes the thermal energy is higher than the energy that you put in, because we might move energy from the cooling side to the heating side. So the COP is the thermal energy out divided by the fuel or the electrical energy in.
That's wonderful. And so the higher the COP, the more efficient we can say the technology is. And we offered this cool graphic that Kristin helped develop that shows a really nice scenario of here's what you get out for what you put in. And then we broke down, these two options on the left. They are a lower COP, and then we previewed for hot water and how that has a higher COP. So now we get to dive a little bit more deeply into how that's possible. And I'm excited to go over that today. Any other thoughts you want to share on this guy? Cool.
No, I think that's a good intro to it.
Awesome. All right. So next up, what I want to cover is what is the reason that how is it that steam is technically this lower COP than hot water? Can you walk us through this idea of heat loss and what happens from the plant to the building?
Yeah, so there are some losses that are just inherent to a steam system. You're going to lose about 20%. That's just because you're doing combustion, which is going to be the case if you're going to do steam or hot water. You're going to lose about 20%. And then for steam, there's another 8 to 10% that you're going to lose to in-plant steam use. And then you're going to lose some heat in the distribution system because you're distributing it at a very high temperature. It's a lot higher temperature than the ground. So you're going to lose a pretty significant amount of heat there. And the 15% that's shown in this example, it could be higher. I've seen 27%, it can be pretty substantial. And then within the building, you have some steam inefficiencies. And overall, you lose 48% of what you put in. So this is an example of, if you looked at the COP, we usually talk about COP for a piece of equipment, but you could look at it for the system as a whole. So this system, I would say, has a COP of 0.52. So it's pretty low.
Yeah. So that heat transfer loss is something that is really significant, that when we're thinking about the amount of energy that we're putting in for what we're getting out. So alternatively, I think it was really helpful for you when you outlined what this looks like when we think about the hot water version of this. Can you walk us through that?
Yep. So you still lose that 20% because you're still, in this example, we're going to keep the boilers. We're going to use a similar boilers type. Now it's a hot water boiler, but we're still going to do natural gas. So we're going to still lose 20% for combustion, but that 8% went away. You're now distributing at a lower temperature, so you have less heat loss. We're going to say 5%. The inefficiencies in the buildings are gone. And now you have energy losses that have been cut in half. So now you're at 24% losses. And now your COP has gone all the way up to 0.76. So it's a pretty big improvement. And that's without doing any major changes within the plant we could do heat pumps or heat recovery chillers. Like there's, all kinds of different things you could do that would make that even better.
Yeah. I want to give a quick shout out to Dartmouth College for this graphic that I borrowed. I'm working with them right now, and we tell this story internally at RMF all the time, so we help develop this. But it's been a really useful thing to kind of see how along that pathway things tend to decrease. So I think my next question for you, Kristin, is, all right, well, hot water sounds awesome. Why don't we do it everywhere? Why don't we just say every client you should go about doing this right now? What are the implications for that?
There's a lot of reasons you might not be able to if you have a lot of process steam. Mostly it's going to be a lot of cost considerations. You'd have to redo all your distribution piping because hot water pipes are generally going to be bigger, and then steam is more corrosive. So you probably can't reuse those pipes, even if they're at the same size as what you need. And then huge thing is building modifications. Usually the buildings are probably going to use a higher temperature heat than you would get with hot water. Because a lot of times when we're talking about hot water, we're talking about low temperature hot water. So if they're taking in, if the terminal equipment for the heating equipment needs 180-degree water, but we're only distributing at 140, then, you need to make some pretty big changes within the building. And that might be the biggest ticket item on your entire project. And then the distribution piping is pretty substantial as well.
That's super helpful. So just to reiterate, you would consider 140 that low temperature hot water and 180 a higher temperature hot water. Yep. And the building to use that low temperature water, something would need to happen to make up that 40 degrees. is what you're
Mhm.
saying. Mhm.
Yeah, and you also have to consider if they just put in brand new steam equipment, they're not just going to throw that out either. Like
Mhm.
you always have to consider every aspect that is involved in a campus.
Definitely. Thanks for going over that. I think it's a crucial decision point for that master planning process of, do we want to head in this direction because of the inherent efficiency gains we will get from it? So, that can be a big determining factor. But the other piece then is, okay, let's talk about some of the technologies that hot water enables. So I'm going to just pull up this slide. Should look familiar to you. We added a couple others since last time, so we tried to simplify what we covered in this slide. But last time, these were all of the decarbonization technologies we looked at, and we wanted to just focus in on which ones hot water pairs with. However, we already went over a couple of these last time, but last time we were talking about them in terms of steam. Some of the technologies we also went over also cover hot water. So ones that we went over were industrial heat pumps, the electric boiler, biofuels. Is that right? I think.
Did you say combined heat and power?
Yes.
And hydrogen, we also
Yep.
did.
Yep. Hydrogen as well. Yep. Thank you. So today we are going to focus in on the few that we weren't able to, or that weren't worth talking about until we were prefacing about hot water. But you also had another point with these. It was that these ones can only produce hot water. Isn't that correct? Yep.
Mhm.
So with that, let's start thinking about some of these technologies and walking through. And before I do, I think it'd probably be good to preface this with the fact that we could have a whole decarb debrief session about each of these technologies and all the complexities that go with them. But what our goal for today is to give you a brief overview of generally how they work, what their pros and cons are, as we established last time, and then also thinking about a schematic of how they might be included in a system as a way to introduce you to these concepts. And let's talk a little bit about the condensing boiler, which is a great gateway option. Can you tell us about that?
Yeah, so this option is going to be generally with natural gas. You could maybe do hydrogen or some other options, but typically it would be natural gas. But you get a lot better efficiency than you would for like a conventional fire tube boiler, for instance. So we're looking at going from an 80% efficiency all the way up to a 94. And it can get even higher than that, because the lower your return temperature, the better your efficiency gets. And the way that they're getting the better efficiency is that they're going to capture some of the heat that comes out in the stack. There's the latent heat, which is the heat that goes into the phase change. And we're going to capture that by capturing the condensation on the boiler.
Yeah, very good. And I'm really glad that you brought up the fact that it's a non-electrified solution, because I think that is something that comes into play a lot with the decarbonization technologies that we are often discussing. Is a lot of times they are electrified, and that has an impact. Can you tell us a little bit more about that piece?
Yeah, so sometimes we run into problems where we can't increase the electric demand, or we're limited by how much we can increase it. So this is an option that does not do that. And it is more efficient than a standard boiler, so it's still a good idea to do. And I mentioned before, you can use alternative fuels. You could use renewable natural gas. You can use hydrogen. So this can be a decarbonized solution too. However, sometimes there are laws that say you can't use fossil fuels, you can't use combustion. And it is the lowest efficiency of all the hot water options that we're going to discuss today.
Yep. So not necessarily a preferred option all the time, but it could be the only option depending on the capacity of the organization.
Yeah. And one of the things we probably should have put in the pros is it's very reliable. You can use it in any weather.
Wonderful. Ooh, quick note on pros and cons. I love this. Thank you for adding an additional, but please do not be fooled by the numbers of pros and cons. Like just because something has 5 pros and one con could be something that is often a deal breaker, or vice versa. So just want to give people a heads up on that, just don't gloss over at the number to assume this is good or bad. There's a lot of intricacies that go into whether or not something is good or bad or the right fit for a client.
Yes.
All right, let's talk about this idea of electrification. Can you walk us through this chart?
Yeah, so a lot of the move to decarbonization is that people don't want to use fossil fuels anymore. And so they want to electrify. And especially because they're saying that the grid is going to continue getting greener and greener. And that's what we have seen in recent years and hopefully we'll continue to see. So a lot of what we do is a move towards electrification, but they need to consider what's an actual reality. So this is their existing electric demands for a year. And the two dashed lines, we have the college-owned feeder capacity and then what the utility company has as well. And the utility company expressed that they are not able to, if they go over that 10,000 kW, that they would have to increase their capacity, and that it might not even be possible. So it was pretty important to keep below the 10 megawatt line.
Yeah, let's look at an example of that.
So if we decided to do the simple solution and just put in electric boilers, then the electric demand goes way high up. And this is, it's not even possible, what was shown here. But if we look at some other technologies that have a better COP, then we can reduce that, we can reduce the electric demand. And here, not only do they not need to increase the capacity for the utility company, they don't even need to do it for the college-owned feeders. So that saves a lot of money, and it also makes the project a lot more feasible.
Yeah, great. Yeah, so let's continue down this road. Here's an example of a heat recovery chiller. I'd like to take a quick moment to talk about this concept of heat recovery. So this idea of heat recovery, a really easy scenario to talk through this concept is thinking about an apartment with a AC unit on the wall. So say we have this apartment and it's starting to get hot in there. Kitty's getting hot. So what we do is we're going to turn on that AC unit. So what happens after we turn on that AC unit is we start feeling cold air coming in. And what Kitty might think, because Kitty is not an engineer, is that that cool AC unit is adding cold to the space. But what's really happening is that AC unit's condenser is removing heat from the space. And so the idea of heat recovery is saying, hey, right now, if you walked past that window outside, you would be blasted with hot air. So what if we could capture that hot that the AC unit is taking out and transfer it to someplace that's more useful? So instead of literally throwing the heat out the window, what if we repurposed it? And so that is a story that can really help people understand heat recovery. Feel free to use it with your clients, et cetera, to help them understand that that's where we have an opportunity to get these really great efficiencies, is to take heat that was a byproduct of something else. Anything you want to add to that, Kristin?
No, I was just gonna say that's a really great transition into heat recovery chillers.
Let's talk about them.
That's exactly what they do.
Yeah.
So what a heat recovery chiller does is that it takes the heat that is rejected by the chilled water system and it puts it into the hot water system. So now we have thermal energy from the cooling side and the heating side. So it makes our COP go up because both of those thermal energies count. So now we have a COP all the way up to 7. And keep in mind, when we were looking at just a plain regular hot water system, we had a COP of 0.74. All right, 0.76, I think it was. So we've gone from less than 1 all the way up to 7 for this technology. But there's some caveats that it only works on simultaneous heating and cooling. So in order for this to work, you do need to have heating and cooling loads at the same time. It's not a storage system.
Yep.
But it is the most efficient of the ones we're going to talk about.
Yep. So that simultaneous piece is pretty crucial, and it can sometimes be hard to understand, but an example would be, so a climate here like Minnesota, where I'm sitting today, sometimes the heat recovery chiller may not be the best fit because in summer, we're doing great. We're adding cooling because the weather is hot. But if we aren't always running cooling, like say in the winter, then we have no byproduct heat to recover to use elsewhere. However, if I'm at a major university like the University of Minnesota, they have labs and things that have to be constantly chilled, so it could work there, but a smaller campus, maybe not. So I think that non-storage issue, it can be a pretty significant issue of why spend the money or the time on this solution if that's not a situation at that specific institution.
The pros are it's the best efficiency you're going to get. It's really pretty fantastic. And it's a fully electric option. And then the high COP, it minimizes the impact to the electric demand. And there is a potential to eliminate cooling towers. I always say cooling towers are not terrible things. They have amazing COPs. They're actually pretty incredible. But you sometimes get a push from clients that they don't want to have cooling towers. So if they are the right client, they might be able to get rid of them. But again, you can only use it for simultaneous heating and cooling. And if you are not the right client for this, it might not be able to supply your peak heating loads because generally speaking, your peak heating load does not happen at the same time as your peak cooling load. That would be pretty surprising. And if your cooling load is not sufficient to supply the heating load, you're going to need something else to supplement.
Yeah. I'm glad you said that about cooling towers and that's because of two things. One is some campuses find them to be unsightly and want to get rid of them. So the heat recovery chiller, if it's an option, they might prefer that. But a second thing I wanted to add is that as a sustainability worker, I've heard at various webinars and sessions that some might think of a cooling tower as a great heat waster, some kind of thing that's tossing that heat that we could recover into the air. However, there is a time and a place for them. So thank you for
they do waste the heat, and recovering that heat would be better.
Yeah.
But just for context, the COP of a cooling tower is about 17.
Oh, dang. All right.
Quite high. I don't think we need to eliminate them necessarily.
Cool.
If you want to do it for appearance reasons, that's different, Yeah.
Cool. Well, let's keep trucking because we've got a few more to get through here. So let's talk about the water source heat pump.
Yes. So water source heat pump is moving heat from some kind of a source into or rejecting heat if it's the chilled water side, but we're going to move it either into the hot water system or out of the chilled water system. And which way you go on that is going to really depend on what your source is. So if you're up in Canada and you have a cold river going by, you might use that for chilled water. If you have a sanitary line nearby, you might use it for hot water. There's DC Water, for instance. They run their whole building off of their sanitary line, which is admittedly huge because they're doing the sanitation for all of DC, but they are able to operate their entire building heating off of that. And this is, if you have it available, it's available hopefully year round. And how well it works is going to depend on the lift that's required. So lift would be the temperature change between your source and the temperature at which you want to distribute. So if you have a river and it's always at 50 degrees, and you want to get to 90 degrees, so 50 to 90, that would be a 40-degree lift, just as an example.
Yep. And I think that the use of a water source heat pump is really interesting that lift is lower than, say, the outdoor air temperature. And we'll get to an air source in a moment, but that is a very powerful technology that can leverage an asset that someone has. Okay, so let's continue talking about the pros and cons of a water source heat pump and how that fits into that schematic.
Yeah, and the way this works is very similar to the heat recovery chiller, because you're still going to take advantage of those simultaneous heating and cooling modes, which you might do with a separate piece of equipment, or you might do it with the same piece, but there's no reason not to do that. And then your heat pump is going to take heat from wherever it has available. So you can kind of see how these interact.
Very cool.
And as far as pros and cons, it's kind of a matter of whether it's available to you. It's going to require proximity to some kind of a heat source. You need a river, reservoir, a big sanitary sewer line, some way to capture your building exhaust. Those things just might not be available to you. But if they are, then they're a great way to capture some heat that you might otherwise be throwing away. And then similar to the heat recovery chiller, it might not be able to supply your peak heating loads. So it's going to be pretty case by case, but it is an electric option. It does not require you to have simultaneous heating and cooling loads, and it's got potentially a pretty good COP. Kind of a typical one that we'd see is maybe like 4.5. So it's pretty good.
Awesome. So just to harken back, we had about a 7 plus for simultaneous, but then 4-ish for a water source heat pump. Less good, but still really solid. So
Well, so the reason why it's less though is because you're only interacting with one system.
right.
So like say if you were doing the water source heat pump for your heating side, and then your chilled water system was doing a water cooled chiller, your overall COP for your system might not be any worse, because chilled water side, if you're doing a water cooled chiller, it's going to be like 4.75. So if you add that to the COP for the water source heat pump, it might even come out to be higher.
Great point.
You have to run the numbers.
So let's talk about something that actually pairs with a water source heat pump, which is this idea of geo. And I'm just saying geo right now because geothermal is the word that people tend to know, but there is a difference between this concept of geothermal and geo-exchange. Would you walk us through that?
Yes. Usually when people say geothermal, what they really mean is geo-exchange. There aren't that in the US, there aren't that many geothermal systems. So what a geothermal system is, it's going to be a single well, and it's going to go way deep down. Cornell is the example that everybody talks about. They went 2 miles deep. So this is a big, big well. And they use it only for heating. On the other hand, we have geo-exchange, and this is what people are usually referring to, where we're going to dig several wells. They're going to be anywhere from 400 to like 800, 900 feet deep. Or horizontal wells, which are not as deep as that. They'll be significantly
Couple hundred, yeah, or
yeah,
maybe even less than 100 in some
no,
cases.
yeah, less.
Yeah.
But typically they're going to be talking about vertical wells, and there'll probably be hundreds of them, especially if we're talking about for a campus. That's what we're usually talking about. And so those are going to be dug into a bore field, and the big thing that you need to take away is that you need to balance your heating and cooling loads, because this is a storage system. So whatever you put in the summertime, whatever heat you reject to the ground, is what you have available for heat in the winter time. You don't have more than that available.
Yeah. And this again is one of those systems that could take a whole seminar or more to really understand. I think Kristin has given a really helpful overview that it's a storage. A lot of people describe geo-exchange as a battery because it is a way to sink heat in the summer and then use it in the winter, for example, or during a temperature change. And it is the solution that we are often seeing in higher education campuses in the United States. So if somebody talks about geo at a campus other than Cornell, who is fancy, it's probably geo-exchange. And knowing the difference between that is important. I want to just throw out there of like, it's not so that we are like coming off as some kind of holier than thou, smarter than thou nerd of like, well, actually it's geo-exchange. It's actually the goal to understand how that system works and what it's actually doing. And the really simplistic way of doing that is, in my mind, geothermal equals a volcano somewhere or something super deep in the ground to get heat, actually extract heat from the earth. And geo-exchange is more of a heat storage solution using the ambient temperature of the earth. So that's in general what we want to come away with today. And let's talk a little bit about some of the pros and cons of geo-exchange, since that's the system we tend to recommend or utilize.
So you're going to need to do a test well, because there's a big variability, even within the same campus, for how much you can actually get from these boreholes. rule of thumb a lot of times people would say is 3 tons per well. So you have to do a test well to see whether it's something that's feasible for your campus. The installation tends to be very disruptive because it's going to take up a whole field or several fields, especially if you're trying to supply your entire campus. You do have to balance it. You can't just only use it for heating. It will eventually stop working if you do that. And then it tends to be very expensive.
Yeah.
However, once it's installed, the maintenance costs are very low. It's pretty much just maintaining the pipes.
Yeah. One thing I want to offer is that GeoExchange is not necessarily a new technology. It's been around for decades, but the feasibility of it was never really sound. You know, natural gas was a cheap heating solution. Why would anyone want to spend all this money on burying all these bore fields? Well, as we talked about in the first decarb debrief, there are some things that are pushing that. One is the Inflation Reduction Act and a way of potentially financing this work. And two is, you know, rising costs that might happen as a result of these fossil fuels eventually running out potentially, or prices going up as things become scarce. And then electrification could result in that decarbonization side, and it is an electrified solution. So that's something that helps us on decarb. So let's look for a second at how this connects with that water source heat pump. It's like another level deeper.
Yeah, so it's we will still take advantage of the simultaneous heating and cooling loads. We're not going to just ignore those. You don't have to do them though, which we'll maybe talk about a little bit later. And then you are going to store heat from the cooling side into your well field, and then later you can pull that out to use for the heating side and produce hot water. But you're also going to probably have to supplement that with something else. And in this case, we used condensing boilers. And for the chilled water side, you might need also additional chillers, which aren't shown here, but could be a part of your system as well.
Awesome. I want to just, we already kind of covered a lot of the pros and cons in just describing how this works, but are there any others that you'd like to highlight here?
It's really just the cost is a really big thing. And you mentioned the IRA, and how that you can get funding from the IRA. There's a lot of it's not as simple as it seems as to whether or not you'll be able to actually access that funding.
I agree with that. Yep.
Yeah, which is it's a lot. It's a pretty big topic. If you aren't able to supply a certain percentage of the usage or the load for your campus, then you're not going to be able to access those funds, is kind of what it boils down to. So it's not going to be something that's available to everyone.
I would absolutely agree with that. Legislators, when they wrote the Inflation Reduction Act, were really focusing on renewable electricity generation sources like solar, wind. Those were very clearly indicated how they could be funded, but GeoExchange was a more tricksy science that they didn't quite understand. So the legislation isn't super clear about how it funds that. A lot of our higher education clients, shout out to Martha, are working to understand and leverage those funds better. So I think that's a really good point. Just want to mention too, the COP of the GeoExchange system, seeing about a 3.5 for that.
Yeah, and then on the cooling side is probably about a 4.5, which is similar to a water cooled chiller. So if 3.5 is going to make the difference for heating, then it might be a really great system for you.
Awesome. Great. All right, let's talk air source heat pump.
So this one is going to be the one that is changing most quickly right now. So if we talk about this 2 years from now, I might have a lot of different things to say, but just some general things. What it's doing is it's going to extract heat from the outside air and put it into the hot water system. You can use it for cooling, but the COP is lower than you get even for like an air-cooled chiller. So you just wouldn't use it for cooling, but just so you're aware that you could. But the COP for heating is going to be better when there's more heat in the air, which makes perfect sense. So the warmer it is outside, the better the COP is going to be. And there is a minimum to how little heat they can handle. Right now, today, they can go down to about 10 degrees or 0 degrees Fahrenheit. That number is changing all the time. It's getting better and better, and COPs are getting better and better. But it is very large outdoor equipment. It needs sufficient clearance. So you need to give it, you can't just be like hugged up against a building because it needs some room for the air intake. And it's noisy. So sometimes people don't want to see that because it does, we often talk about minimizing the appearance of equipment on campus. This does not minimize it.
Definitely. And I'll just do a quick glance at how the air source heat pump might work into a schematic for heating and cooling option.
So this one's pulling its heat from the air. That's kind of the big takeaway.
Yeah, great. And then let's just talk about a couple of pros and cons. Again, you already covered it, but I do want to just highlight that fact that right now that it's sitting at about 10-degree minimum outside temperature. So here in Minnesota, there would be several months, well, up to a few months of the year where you wouldn't be able to leverage that air source heat pump. Is that accurate?
Yeah.
If it's
it's not always the right solution,
right.
Or maybe not for the entire year, but it might be a good solution during the shoulder seasons.
Right. Great. Any other thoughts on that? Because we got a few minutes left. I'm going to keep pushing forward here.
Yes.
So now let's talk about some getting a little bit more complex in how we might do our approach.
So the next thing to talk about is ambient loop, which you may have heard about, and people have a lot of misconceptions about. So, this could be really an entire topic very, very easily. But basically what it's going to do is it distributes medium temperature water. I'm not saying medium temperature hot water. It's going to be somewhere 60 to 90 degrees. And there's going to be a loop that goes around your campus that distributes that. From there, it's going to interact with a water source heat pump that is in every single building. And that's the fairly big piece of mechanical equipment. And from there, the temperature will get boosted up to be hot water or lowered down to be chilled water. It is a single pipe that serves both the heating and cooling. And you can also do simultaneous loads from it. So the water source heat pump in the building will do the simultaneous heating and cooling there. And you'll see a similar COP to use did for a heat recovery chiller, about 7. And then the really cool thing is simultaneous loads for the loop that are not within the building. So like if building A is in heating and building B is in cooling, and we can transfer some of the heat from B to A, you don't need to run any equipment because what you need to do is keep the water in the loop at the same temperature. So heat's getting pulled from one building, pulled on one side, and then put in on the other side. And you don't need to run any mechanical equipment.
In that heat recovery idea is something that is we're transferring from building to building now instead of at the plant level. Is that right?
Both. Okay. You're doing both.
Yes. Yes.
But it takes a lot less heat to get to 60 to 90 degree water. So now, if we talk about what kind of technologies can provide that heat, and heating is kind of always the harder one than cooling. Those air source heat pumps that we said they can only go to a certain temperature, they can now go to a lower temperature and they can provide a better COP. So air source heat pumps a lot of times become a pretty big player here. You no longer need a chiller. You can run purely from a cooling tower. Can you go to the next slide, Wendy?
Yep.
And what we're showing here is just that every single building has that water source heat pump. And from there, we're going to do heating and cooling. If we go to the very next one, that's kind of more going to tie into what I was saying.
Yep.
You can get your heating and cooling from just about anything. It could be renewable heat sources, all these things that maybe didn't provide enough heat before and now can do enough. And one thing that's shown on here that we don't really talk about, but it comes up with ambient loop a lot. You can use several different sources. They don't all have to be located at the central plant. And people often say that that's like the big deal with ambient loop. And I always say that's the smallest deal with ambient loop because you can do that with any system. You could put a boiler in every single building and interconnect them if you wanted to.
I'm glad you mentioned that because I definitely, and I'm really glad that you covered this in this presentation because I definitely had a bias against ambient loop. I was like, that's dumb. District energy is cool because you're keeping all your maintenance in one place. And I was pretty ignorant of the idea that you do have all that mechanical equipment per building anyway. So what it does add for maybe a complexity of having the water source heat pump at the building level, it does
Yeah.
add in a ton of opportunity that you could give. So that's really
Well,
cool.
and it is a significantly more complex system. If you go to the next slide, we'll talk about the pros and cons.
Yeah.
The high system complexity is one of the biggest things. The water source heat pumps are going to be a different size for each building, so you can't just swap one in for another. There's so much more mechanical equipment. And if we're looking at an existing system compared with a brand new system, it's a pretty good system for if we're putting in something brand new. But I think we all kind of know we're usually dealing with existing systems. And do the mechanical rooms actually have space for that much equipment that's a big question.
Right. So I think this visual does kind of help with that of like suddenly we're transferring, what did you say, 70 to 90-degree water through this green system here.
Mhm.
And that requires like that idea of like newer infrastructure makes more sense to set this up rather than existing equipment. Yeah.
Yeah, but if somebody says, I want to put in a brand new system, then I think this is something you should absolutely consider.
Very cool. All right, so just want to harken back to this slide from a past deck of we're always trying to balance this idea of cost, energy, and carbon when we are picking the portfolio of solutions that we are doing for a client. But I thought that I think quickly we could just run over this in a couple of minutes, this idea of the cascade of mixing technologies. Can you walk us through this as a closing thought?
Yeah, so you mentioned that there's a portfolio of solutions. It doesn't have to be just one thing. We talked about air source heat pumps and water source heat pumps. You could use them together. So if you really want to use an air source heat pump, but it can only do a 100-degree lift, you could produce 100-degree water and then have it interact with a water source heat pump that's going to lift it even higher to say 140 or maybe higher than that. Or alternatively, instead of cascading, maybe what you need to do is to look at what kind of usage does your campus have. Can you go to the next slide?
Yeah.
You might want to say, I'm going to use my geo-exchange heating only during a certain season of the year and really maximize that as much as I can because I want to decrease my heating demand that would have to go to something like condensing boilers, and so you can or to electric boilers. You don't want to increase your electric demand, but then you want to use your heat recovery chiller. You could alternatively choose not to use the heat recovery chiller at all and store all of your cooling, all of your heat from your cooling system, and then increase what comes out of your geo exchange even more. But another client might say, I'm going to put in heat recovery chillers because I'm in North Carolina where it's nice and warm. And then the remainder of my load could be covered by air source heat pumps because it's never below 10 degrees there. And then they can use a pretty efficient system with water-cooled chillers for the remainder. So the solution is really very rarely one single technology. It's going to be a mix most of the time. And what we really want to know is what is the overall COP of the system. So if we go to the next one, this is showing the COP of all the different technologies that are being used. And then on top of these columns, we show the COP of the entire system. So while the buildings see the same amount of energy or very close to the same amount of energy that's being produced for them, the amount of energy that goes into that system is pretty drastically different. And so the ambient loop is that last one there. That's going to be your best COP. But, and that's kind of a cool, trendy one people always talk about. But air source heat pumps that get a lot of bad press, that COP is 2.04. It's actually pretty close to an ambient loop, which is pretty cool.
Yeah. And I love this idea that, if simultaneous is an option, and because that's the highest COP, we want to be running that as much as we can, and then we start switching. So like the idea of geo exchange, like we run simultaneous as much as possible, and then we switch to geo, which is slightly less of a COP for this part of a shoulder season. And then when it's another season where we're in, core heating and cooling mode, we might then go to air source heat pump next or something like that, depending on the weather or that sort of thing. So, trying to line up these players to be active when they're most efficient is a really interesting concept that you all plan so well. So,
and that's why we look at things on an hourly basis.
with that, I am seeing we are getting close to the hour. We only have a couple of questions in the chat right now, but I want to open it up. I'm going to stop sharing so that you can see our faces. But thank you, Kristin, so much for all of the time and effort you put into this presentation. I think it's such a good overview of the work that you're doing. Caroline Fitzgerald asked if RMF has designed an ambient loop system, and Andy replied, not yet.
Nope.
But it's definitely in our arsenal of opportunities. And again, I think one of the challenges there, as Kristin said earlier, is it really needs to be a new campus. And I don't know that, how often would you say that we're helping design a new system rather than retrofitting or improving a past, from your experience?
Almost never.
Yeah.
It doesn't have to be a new system. It's just much more likely to work, because it's just a matter of, do they have room in their mechanicals? Do they have room in their mechanical rooms? There's a really good chance they don't.
Yeah, that's fair. What sort of pipe size increase do you see from steam to hot water, Kristin?
Maybe roughly double. It's going to depend on your temperature difference. Like that's, but if you're going to a 20-degree delta T for the hot water side, it's going to be about twice as much. John made a good point that it's a bigger increase from the condensate side. So the hot water side is going to be roughly double the steam, but you need a supply and a return line.
Andy asked the question, do you have specific building design temperature you want for the district option?
I was going to say the temperature that you design to is going to be very case by case.
Yeah.
It's going to be a question of like, what do they currently use? Is a lot of times we see 180. Do you care if it is low temperature or 180? Yeah, of course. Because if it's 140, there's a good chance you have to redo a lot of the equipment that's in the buildings. Pulling that out, there might not be room for bigger equipment that's needed for 140 degrees. And the thing is that the technology is evolving a lot. So right now, it's a lot easier to produce 140 degrees, but just in the last year even, all of a sudden there's a lot more people who are saying they can do 170, 180. So that's why I didn't really get into too much of saying low temperature hot water, because a lot of times now we're talking about medium temperature hot water, which would be like 180 to 200 degrees.
Yeah. That whole picking a temperature thing can be a really sticky point yes. Because that has a lot of impacts. John Williamson asked, how much does a bore cost for GeoExchange? Granted, depth and number would impact, but a high level estimate. I think you've said a range.
Yeah, it's a really big range. Like I've seen 60,000 and I've seen 12,000.
And it depends on how deep you're going.
Yeah.
It depends on where you are in the country and how like in demand a driller is. They could maybe, like, I hate to say price gouge, because we want to think the best of our vendors, but if they're in such high demand, there could be a wide variance. It's interesting because I was having a conversation last night with some folks about Darcy wells, but what it is it's a submerged geo well that is less deep, and the heat pump is in the well somehow. I'm obviously not presenting on this super well, but because of that, it doesn't need to go as deep. And one of the drawbacks of it is that it has ventilation that is above ground, so it can't be fully buried like a bore field. But at any rate, one of the reasons that it is starting to get traction around here where it's been invented is because you could use like an actual well driller to be your driller and not a bore field driller. So there are some reasons that new technology is introducing ways to be competitive in these bore drilling operations. So anyway, that's just a little hot off the press comment that I will talk with you more about when I know more of what I'm talking about, but it's really interesting. All right. So with that, I'd just love to thank Kristin again for all of your great work prepping for this conversation. Kristin, I think that we'll probably be seeing you again for some things in the future as we continue to think about what people want to hear and dive into a little bit deeper in terms of these various technologies. But thank you so much for the introduction. So with that, thanks again, Kristin, and thanks to everybody for joining us today. What a great conversation, and we'll see you next time. Take care.
Bye. Thank you.
Bye.